Alright, let's look at the homework on 585 together. Sample problem A. A charge moves a distance of 2 centimeters in the direction of a uniform field whose magnitude is 215 newtons per coulomb. As the charge moves, its electrical potential energy is decreased by 6.9 times 10 to the negative 19th joules. Remember when I had the notes up there with Bob and the boat, and I said if you go with the field you lose energy? Well, this is what it's talking about. It's going with the field, so it's losing energy. Find the charge of the moving particle. What is the potential difference between the two locations? So, first of all, let's look at what's given. The change in potential energy is negative 6.9 times 10 to the negative 19th joules. Distance is 2 centimeters. They changed it. Electric field strength is 215 newtons per coulomb. Find charge, find V. So, part 1. Find the potential energy. So, potential energy equals negative QED. We're trying to find Q, so we will divide ED over, and the negative for that matter. So you look, and they did that. They divide the negative and the ED over, substituted in their numbers, and they came up with this, the charge of 1.6 times 10 to the negative 19th coulomb. So it was a proton. Then they asked us to find the potential difference from the 2 points. Let's see if I can draw here. So they're saying the charge, proton there, moved from here to there, from this spot to that spot, and that was the D that we talked about. And they're saying what is the voltage from this point to that point, regardless of what the charge is doing. What's the voltage from here to there? Let's go back to the textbook. And all they do is say negative ED. So 215 and then the distance, 0.2 meters, and multiply. And there's your voltage. That's all you do for that problem, guys. Okay? So now let's start looking at the actual problem. See if I can lift that up just a little higher. Alright. So number 1, as a particle moves 10 meters along an electrical field with this strength, 75 newtons per coulomb, its electrical potential energy is decreased by 4.8 times 10 to the negative 16th. What is the particle's charge? So it's decreased by that amount, so we're probably going to put in a negative with that. And I did not include a negative in my little thing I gave here. Let me check it in there. Negative. So, first problem. 10 meters, 75 newtons per coulomb. Here's the charge. Find Q. So we want to look here. A distance, an electric field, an energy, and a charge. That seems to be this equation here. Potential energy, Q, E, and D. It would appear to me that we're probably going to divide this stuff over, and that negative also is going to have to get divided over. So an extra negative over here, and that'll give us a positive charge of some amount. I'll let you solve that. Going on to number 2. What is the potential difference between the initial and final locations of the particle in problem 1? Well, that's just like this here. From this point to that point, and in this problem it's 10 meters. From that point to that point, what's the voltage? So you get the voltage equals E times D. Hey, I don't want that D, I want this D. There's the D, there's the E, bada boom. The voltage is 750 volts. Then let's look at number 3. An electron moves 4.5 meters in the direction of electric field strength with that much 325 newtons per coulomb. Determine the change in electrical potential energy. So let's see here. We've got a field, we've got a charge, and we've got a distance, and they want to know change of potential energy. So again, it looks like we're using this equation here. Change of potential energy is the thing we're solving for. E, D, and throw in the charge of an electron, and it would appear that you're going to get your change of potential energy. Alright, let's go here to the online text and look at the next questions, 5 through 8. Turn one page, turn the other page. I hope you guys are using this online textbook. It's kind of nice not to have to lug a book around. So look in here, number 5. A uniform electric field with a magnitude of 250 newtons per coulomb is directed along the positive x-axis. A 12 microcoulomb charge moves from the origin to this point here. So they've got here for you, they got the origin, 0, 0, moving up diagonally to this point. So you're going to have to make a triangle with number and number to find how far it really is when you're doing this problem. What is the change potential energy? And I think with field and charge and distance, you can do that. Number 6 was change the electrical potential energy of a lightning bolt with charge, distance, and field. There's the information you need right there. You guys got to solve it. Number 7, the gap between electrons and spark plug is 0.06 centimeters. They're very, very tiny. Producing a spark in your thing that's 3 times 10 to the 6 volts per meter. What is the minimum voltage that must be supplied to ignite the engine? So check it out. You got volts per meter and you got a distance, and we want potential difference. Kind of hit clear this stuff out here for a second. So we got volts per meter, and we've got what we got here? Volts per meter in a distance, and we want voltage. Volts per meter. An electric field of volts per meter. Electric field, that has a different unit. That's why it's a little weird. Newtons per coulomb, volts per meter. Guess what? Those are equivalent units. So you have E and D, find V. E and D and V. And number 8, a proton, they have charge right there, is released from rest in a uniform electric field with a magnitude of this. So there's your field again. The proton is displaced by this. Find the potential difference of initial and final positions. So they're asking you to find voltage here and find the potential energy as a result of that displacement. So guys, you're just manipulating the same equations over and over again. Alright? Good luck with that.